Hello and welcome back to Calculus 1. Welcome to the end of chapter 2, 2.7. The book calls this the precise definition of the limit, like there is an imprecise one. So this is going to be the epsilon delta definition that was designed by mathematician Weierstrass in 1850s, almost 200 years later. After Newton talked about the derivative and stuff. Funny that the derivative and integrals were both defined and used before the concrete definition of the limit was given. And today we have both definitions for the limit and integral in terms of, for the derivative and integral in terms of a limit. So now, what is this, this statement? So, limit of f of x as x goes to a, assume f of x is defined at all points near x equals a, except possibly at a. Then limit x goes to a of f of x is equal to L if for every number epsilon larger than 0 there exists a number delta larger than 0 such that f of x minus L is less than epsilon whenever 0 less than x minus a less than delta. That's it. That's it. What's 90% important? This. What's the other 10% important? Right here. So this is what we have been doing the entire chapter 2. And this is the definition. First, I will ease your pain with epsilon and delta. Those are letters from Greek alphabet, just like pi is. So pi is equivalent to our P. Epsilon is E, and delta is D. So those are just letters from Greek alphabet. So you have delta, and you have epsilon. Lowercase d, lowercase, all right. Uppercase, that will be delta uppercase, and no, E is just a regular E. The summation is S. Anyway, we don't need the uppercase, so that's it. Now what we have here, to understand what this means, I'm going to draw, I'm going to put this somewhere else. I'm going to draw the picture. And this is the same one that you have seen 5,000 times so far. So I'm just going to draw some function f of x. Arbitrary. I'm going to put my a and its corresponding L. So now I'm going to draw deltas. So this distance is delta, meaning a minus delta here and a plus delta on the other side for these 3 points. A is in the middle. Now when the red line hits the function, it bounces into y. When the blue one hits the function, it bounces into y as well. And those distances there are epsilons. and you have your L minus epsilon and L plus epsilon. What this creates is a tube around the black line. And what these things do, they're squeezing. So epsilon and delta are extremely small numbers. Extremely small numbers. And you can make them, in fact, as small as you want. Right? In nature, as we do sciences, we care about the Planck's constant and right, Planck constant at the order of 10 to the negative 30, negative 10, 32, 33, right? Atom size, 10 to the negative 15, right? There's nothing in the book that says that you can't make epsilon to be 10 to the negative 300 or negative 1 million. Those would be so small, right? So we don't put the cap on how small we can make these values. Now, a statement like this, what would this mean? Well, note that you have F minus L. F minus L is the difference in between F and, right? So this value is your X, which is getting closer to A. So that's the red line is the one that it's moving closer to the black line. Therefore, the red line over here, which is L minus epsilon, is the one that moves closer to L. So your red line, this one, red line is your f of x. So the difference between L and f of x is that epsilon. So I hope that you can see, in terms of mathematical terms, the squeeze. Because as you are making the difference, as you're making the difference smaller, because you have less than, you're making it smaller than some arbitrary very small number, you see that on the x-axis, that is also the case. The difference between these two is also getting smaller and smaller than some arbitrary very small number. So as you squeeze one, the other one squeezes as well, and that's why we say that the limit of A is L, because as you squeeze the tube on x's, the tube squeezes on a y and collapses into L, and that's why that will be the answer for the whole thing. Does this make any sense? So you squeeze one, the other one squeezes, and the way to mathematically denote that is this definition, where these epsilon and delta are positive but extremely small numbers. So you actually, in those proofs, you get to pick one and compute the other one. And then in the proof, you would just say, if we pick epsilon, that it's smaller than blah, 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 the delta would be smaller than blah, 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 and that's the proof. It's a very simple thing. It's very structured. If you just read 2 or 3 of those examples, it should be immediately. You don't have to be the math major or math genius to understand it, because you are literally looking for as small as possible value, the largest small possible value that you can use to satisfy the inequality. That's technically what it is. So as we squeeze on x, we get a squeeze on y, and everything collapses. The red and blue, they collapse on the black line in both cases, and technically that's it. Let me just put the delta and epsilon. So we have those. The second picture that you are responsible for is going to be this 1 over x graph. We are going to use our a at 0 in this case, and you know that this picture will be no limit, right? So what happens? As you approach from left and right, look what happens. You have your a plus delta with a delta, and that's a minus delta on this side, and a plus delta on this side. So your x-axis now looks the same. as the x-axis up there. But your epsilon on the y-axis is creating these two values here. Let's call them L1 and L2, I don't know. Now what happens as the delta goes in? As the delta goes in on both red and blue, your L1 star, let's say, and L2 star are further apart. So you see that as you squeeze on deltas over here, in the y's, instead of collapsing, they go apart. Do we see that? So the first iteration was when delta was this far away, the y values were this far away. When I squeeze in on delta, the epsilons, instead of going less than, they go more than, right? So the limit does not exist because it doesn't fit the definition. Definition says that both of these need to be getting smaller and smaller so we can pack them in a very, very small numbers. But do you see that the y values are going to go infinitely apart? Well, that doesn't get to fit in less than, let's say, 0.10 to negative 3 or negative 6 or whatever. So in this case, limit of f of x does not exist on the second one, right, as x goes in this case to 0. Because, again, the more you squeeze deltas in, epsilons, instead of being infinitely small, they become infinitely big. Let me write that as a statement here. So in this picture, as deltas get closer, epsilons go far apart. That's good enough, I guess, to understand the concept. And epsilons going far apart is violating this, right? That's violating that. So that's why there is no limit in that case. Over here, maybe we can write as deltas go close, epsilons go close. So limit of f of x is L as x goes to a. So that's our standard limit. It works. The second one does not exist because as you push in on deltas, epsilon shoot away from each other, violating the less than epsilon thing.